Hello? Am I audible?
Yes, sir. Yes, sir.
Let's start. Let us start today's work. In the last class, we have discussed with modulus of rigidity to a certain extent. We know in our early strength of material classes, what is the definition of modulus of rigidity? It is the shear stress is proportional to the shear strain, where the constant of proportionality is defined as the modulus of rigidity of a particular material itself. Now, we know, I have discussed a number of times that in our elementary strength of material, we have discussed everything in terms of average stress and average strain. Means for a stress, a load applied to a particular cross section, load may be tensile, compressive, shear, what is it may be. The average stress induced in the cross section is we have taken into consideration. But in actual practice, what we have seen in class and in course of time, that the force never become equal across a cross section itself, and then somewhere it is higher, somewhere it is lower, somewhere it is equal to the average stress itself. That stress can be shear, tensile, compressive, or even shear. But if you design your member according to average stress, it is vulnerable to the stresses which is higher than the average stresses itself. So you have to know what is the maximum stress, what is the minimum stress, and you have to design according to the maximum stress itself. That's why you have generated this stress cannot be measured, is maximum, minimum across a section where there is a multiple, infinite number of particles or points involved. Depends on the size of the cross section itself. You cannot measure it that accurately. So you have to use the help of equations to calculate the maximum value of the stress when this necessary itself. Now, so for modulus of rigidity, we are supposed to go. We have to know what is the volumetric, what is the your shear strain, and you have to know shear stress if you really want to know what is the modulus of rigidity, etc. Now let us start with the coordinate axis OX, Y, OZ. It is the Cartesian coordinate axis. Its origin is O, and it has one axis, it's very familiar to all of you, along x-axis, and it's one y-axis, and everything along z-axis itself. Now, for the benefit of our classes, for the benefit of our calculations, or the reduction of the huge number of constant invariants are there, to reduce them to a certain extent for our own convenience, what we decide that this OX, Y, and OZ are coinciding with the principal stress axis of that particular, say, item going through the particular item, etc. Now, and thus, what we do for an isotropic body where the properties doesn't change according to the position along the surface, but everywhere the properties remain same. So principal axis will be along OX, Y, OZ now, where we say maximum stress will be on OX, maximum minimum will be OZ, and in between will be OY, etc. Now, we are considering another, but it is not customized, that always we will have principal stresses. You know the principal stress and principal strain, and you can use accordingly. We have to do with a practical system where the origin, or where first may be origin, maybe the axis does not matches with the principal stress itself. Then how will you calculate your remaining stresses? By using the principal stresses, etc. Why you are using principal stress? I am telling you very clearly that principal stress axis is acting on certain planes where this principal stress means the measure stress or maximum stress, and it should be tensile or compressive in nature and should be minimum, which is that's also tensile and compressive nature. And on this plane, there is no shear stress acting over it. So shear stress concerned on the particular plane is absolutely zero. So that's why you have taken into account that we are using the principal stress and principal strain concept accordingly. Now, say let us consider another orthogonal frame of reference. That is another Cartesian components. Orthogonal means their line of action or their lines, they have mutually perpendicular to each other, like this OX, OY, and OZ, etc. So there is another orthogonal plane whose originated from the same origin O. Here O, Y, OX, here also OX dash, OY dash, and OZ dash, which means this angle OX dash has an inclination with OX, OY, and OZ. OY dash has an inclination with OX, Y, OZ, and similarly, OZ dash also have an inclination of OX, Y, or Z, but with the condition that they are originated from the same point O here and O here. The origin is same. Origin is not shifted here just to reduce our calculation a bit less complicated. That's why origin can be shifted, and we can add that coordinates of that new position with the result itself. Now, as OX, OY, and OZ are say originated from OX dash, OX dash, Y dash, and OZ is originated from the O, and but it is not matching with the principal stress axis. Okay, it's a normal difference axis there. So, but all this OX has direction cosine of all these OX dash has different as direction cosine from OX, Y, and OZ itself. So this direction cosine, because this is intended at an angle with x-axis, principal x-axis, principal y-axis, and principal z-axis always. Just so they have all individual OX dash line is being have a direction cosine with this, which is at nx1, ny1, and nz1, which is this angle. This OX dash is intending an angle with OX, Y, and z. They are maybe same and maybe different. We are assuming they are different, and their cosine is equal to x1, nx1, ny1, and az1. Similarly, same is the case with OZ. Same is the case with OZ, OY dash, where direction cosines are nx2, ny2, and nz2 here. And same will be the case with OZ dash, like X dash and Y dash, but we'll discuss it afterwards. Now we are dealing with on these two direction cosines, etc. What we have here, we know this is their orthogonal frame, means their in between angle between this frame is 0. In between angle between the axis is equal to 0. So we know if this O dash dash is 90 degree to the Y dash, then their cosine multiplication of their cosine vectors is equal to 0 itself. So nx1 multiplied by nx2, ny1 multiplied by nx2, ny2 nz1 multiplied by nz2 is equal to 0 itself. This is the condition we'll require very soon. Now, say in the coordinates axis O x dash, y dash, z dash, say we have a normal stress acting over any plane, which is limited by an angle sigma x dash, and on the same plane there is shear stress tau x dash, y dash itself. Here in this coordinates O x dash, y dash, O z dash, shear stress exists because it is not principal coordinate, principal axis, or principal plane itself, which is where principal plane is OX, Y, and OZ, and it is inclined. The new Cartesian coordinate OX dash, Y dash, OZ are inclined to a certain extent to the OX, Y, or OZ, which is given by that direction cosine itself of the respective axis itself. So what happens to this if we imagine in the plane who has a normal with sigma x dash and who has a shear stress, how we have got it from the Cauchy's formula itself. The resultant stress vector on the x plane, there is a resultant stress vector. which may or may not be normal to the x-dash plane itself. But we have one normal there, because we know, we have discussed during the stress revision, every plane has defined by its normal in it, or every normal is defined by the plane over which it is normal itself. So this has normal, and we have a one stress parallel to the number which is equal to sigma x dash, another shear stress normal to the, 90 degree to that normal, tau x dash y dash, means it is situated in the x dash y dash plane pointing towards the positive direction of y dash itself as per our sign convention. And we can write down sigma xx dash, but we are writing only x dash because this is the tensile stress acting along positive direction of x-axis itself. Now what happens? Now we have resultant shear stress. Resultant stress vectors in the x dash plane, and in the x dash plane we have components like tau, this should be x, wrongly written, tau x nx sigma I, tau y nx into ny1 is sigma 2, and tau z and tz, not tau, tx ty tz, nx1 into sigma 1, ny1 into sigma 2, nz2 to sigma 2, sigma 3, where sigma 1, this is not I but 1, sigma 1, 2 and 3 are the principal stresses in along x, y and oz axis. And as we know, our x dash axis is inclined, has position cosine nx1, ny1 and nz1. So the resultant stress vector will be multiplied by our sigma 1, sigma 2 and sigma 3 to with respect to this direction cosine, which is intended by it with x-axis, y-axis, or z-axis itself. Now, these are the components in x, y, and z direction itself. The normal stress in this x dash plane is obtained as the sum of the projection of the component along the normal itself. So, sum of the projection of the components along the normal. And you know, the projection, already we have this stress is the force is equal to nx1, nx1 sigma 1, nx2 and sigma 2, and y to sigma 2. So their individual projection will be found by multiplying again with the direction cosine or cos value of the cos theta of x dash to y axis with x, y, and oz, and thus this becomes sigma 1, sigma 2, and sigma 3 square itself. Similarly, the shear stress on this x dash plane in y dash direction is obtained as the sum of the projection in y dash direction, which is in direction cosine nx2, ny s dash 2. In the similar discussion, we have nx1 sigma 1 multiplied by x2, just n has, this is wrongly written, is nx2, ny1 multiplied by ny2, nz1 multiplied by nz2, sigma 3, sigma 2, and sigma 3 itself. So we have got the normal stress and shear stress on the basis of on a plane which is indented at an angle, which is which has a normal which is equal to sigma n, which is same as sigma x, and in terms of the principal stress itself, and in terms of the direction cosine, which the angle ox is intended to make ox is intended to make ox, or reverse vice versa, and y with y, etc. At the same time, if we consider the EPSA 1, EPSA 2, and EPSA 3 in the principal strain, which are also again x, y, and z direction itself, means along the principal stress direction, etc. The normal stress again, which is not the normal strain in any angle x dash, which is not along the principal stress but on other arbitrary stresses are in the coordinate itself, will be given as exs dash is equal to nx square e1, e2, a2, a3, etc., which I've already proved in earlier equation. let me change the page. 4, 5. Just 1 second. Only 2 participants. Okay. Thus, the shear strain is obtained from this equation number this thing, which is the rate of change of angle in between two straight lines, say P into y and P into r, which is after deformation by the action of external force to take the form of P dash into y and P dash into r, and the change of the angle, which is the strain itself, shear strain itself, given by the definition gamma x1 x dash y dash plus 1 plus 1 plus x dash plus by y dash is equal to 1 plus nx1 2 into nx1 nx2 epsilon plus ny2 epsilon 2 ny epsilon 3 itself, and plus nx1 nx2 ny1 to nx3 itself. Now we know this epsilon 1 dash epsilon y dash in comparison to 1 itself is extremely small. So if we set separately this portion is equal to 1 and separately this portion equal to 1 itself. So this will become only 1. And the second terms of the equations nx1 nx2 plus ny plus ny2 nz1 nz2, we have derived that this is equal to 0. This is the multiplication of direction cosine of two 2 sides which is at 90-degree angle with each other. Thus, this equation becomes gamma x dash y dash is equal to 2 nx1 nx2 and 2 nx1 plus 2 nx2 epsilon 2 nx1 nx2 gamma etc. itself. Just a second. Gamma x1 yes, so this will be equal to gamma x1 etc. Now if we substitute the value of epsilon 1 sigma 1 sigma 2 and sigma 3 from the equation ABC, where sigma 1 is given by lambda into delta plus 2 into mu into epsilon 1, sigma 2 lambda into delta plus 2 into mu epsilon 2, and similarly lambda into epsilon 2 into mu epsilon 3 here. So we are replacing all the terms of x1 xy1 with these terms as in the terms of E1 E2 and E3, which is nothing but the principal strain itself. So thus we have got equation will becomes nx1 becomes equal to this nx1 equal to 2 will go down, okay, nx1 into nx2 into mu into gamma plus we put this value as epsilon itself. That's why it is put everywhere here. This is the value of epsilon 2 epsilon. Okay. The, Then if you simplify it further, this equation will take this particular shape. Lambda into gamma 1 multiplied by this one, 2 into mu multiplied by this one itself. Hence, again, from equation 5 to 7b, what we'll have 2 mu into gamma x1 itself, equation 5 to 7b, gamma, this is gamma. So what you have, the tau xy, we are just replacing the full matter here. From here, we are replacing the matter here. And where ns1, ns2, ny1, ny2, etc., these are all again eliminated as it is equal to 0. We have this proportional here. So this portion again becomes 0, and this portion is equal to gamma mu 2 into gamma xy y dash. So thus tau xy y dash x dash y dash is equal to mu gamma x dash y dash itself. So we have got a relation between shear stress and shear strain, one x and y direction, x dash and y dash direction. Now here the rectangular shear strain is given on x dash y dash with the rectangular shear strain is x dash gamma x dash y dash itself. With the relation in elementary circumstance, we observe that mu is the modulus of rigidity, is usually denoted by G itself. So here this term mu actually the modulus of rigidity itself, as per our old idea between shear stress is proportional to shear strain itself. Now, equation 3.8 relates the rectangular shear stress component to xy axis itself. With rectangular set related with tau xy to the shear stress component gamma xy, but this with relation, I just told you, by taking another axis OZ. Now we have to take to consideration of the third Cartesian coordinate axis OZ dash with O xz y dash z dash direction, and we have it will also have direction cosine nx2, nx3, ny3, and hz3, and it is also right angle to ox dash and y dash. So because ox dash y dash and z dash is an orthogonal set of axes itself. So the equation similar to 6 and 8, we can get the relation between now. So one cannot get equation similar to sigma x and sigma b with a equation like this. So here y dash we have put n x2 squared by z1, sigma is the component of the normal stress along sigma y dash, this to this plus this z2, and where z dash is equal to n x2. Z dash, yes, Z dash is to like this, and tau y dash we have defined, discussed in the same way. Is all depending on the matter of the cosine direction cosine itself, because once it was along the normal stress component of normal stress along, we have got the component of normal stress of a resultant stress acting over a plane itself, which is normal to x, y, z, and which has not a normal in Cartesian coordinate system at ox dash y dash z dash. Okay, then the resultant stress has one component along sigma n and another component that is normal to the parallel to the sigma n, parallel to the normal n, and tau n tau parallel to the substance itself. And this resultant stress have a components along ox and y and oz axis is equal to tx into nx, ti into nz, etc. And tx itself can be divided by the Cartesian coordinate sigma n1 into nx itself. So if you replace all cx here, then we'll have this nx1, nx2 square and n3 like this here. And for the shear stress, following the same argument, we have to put this element here. We have to put these three elements here like this. Stop share. Thus, we have tau z was, etc. And following the same equation 7 and b in our other rectangular strain components, we get epsa yy, epsa zz is equal to epsa 1, epsa 2, epsa 3, etc. in terms of with the Cartesian with the cosine vector nx2 and ny3 and z3 like this. And we also have gamma or shear strain 2 into nx m1, ny2, n3, etc. And in fact 2 into nx3 and 1, and gamma x yx is like this here. Now, again, we know sigma x dash, we can put the value of, just 1 second, the value of sigma 1, 2, and 3 here, sigma value of sigma 1, sigma 2, and sigma 3 here in the sigma x. So it will be reduced to take this particular form here, and here. Here S is equal to 1. So gamma lambda into gamma plus 2 into mu into this is equal to epsa xx itself. Similarly, one can also get epsa y dash is equal to gamma into 2 into mu and y gamma z and lambda 2 into mu into the epsa zz itself. So an equation B as per last equation in terms of xy axis, here also z axis, yz axis, tau z axis, we have mu gamma yz, gamma tau z itself. So equation 11a to c and 12a, 12b relates the 3 rectangular shear stress components to 6 rectangular shear strain components, and in this only 2 static strains are involved. Therefore, the Hooke's law for an isotropic material involves 2 independent reactive components, gamma and mu itself. Here, we have to use this typical constant gamma and mu, etc. like this. That is for 5, 6. Now let us go for bulk modulus itself. Now, similarly, following equations, matter 6 equal all the equal 7. Now, we know what is this 11A and B and C equation. I'm just telling you. So in level A and C, we have one of them sigma x dash, the stress, and stress and stress is in terms of strain, sigma x dash is lambda into gamma plus 2 into mu e epsilon x dash y dash itself. Similarly, signal y dash, and similarly sigma z dash, and we add them together, and left hand side is sigma x dash plus sigma y dash sigma z dash, right hand side is 3 gamma into lambda plus 2 into mu plus what happens multiplied by epsilon x dash epsilon y dash and epsilon z dash dash. So we got the in terms of 3 stresses x y z direction and 3 strain in x y direction, but not these are not principal stress itself. Now we know that x1, x2 and x3 is equal to L1. First variant of the stresses is equal to L sigma 1 plus sigma 2 plus sigma 3. And epsilon x is equal to Z1, epsilon x dash y dash epsilon y dash epsilon z dash is equal to J1 is equal to epsilon 1 plus epsilon 2 epsilon 3. So we get this relation, can use this relation accordingly. This equation 13 can be written as in several alternative forms as sigma 1 plus sigma 2 and sigma 3. We have 3 gamma per 2 mu plus gamma if we add them together, and if we again add them with sigma 1 plus sigma x plus sigma z, if we act this way, we will get 3 lambda by 2 mu into z. So L1 thus becomes 3 into mu plus epsilon divided by multiplied by J1 itself. So delta is the volumetric strain. The definition of bulk modulus given as K, pressure divided by volumetric strain. Pressure is equal to internal pressure equal to P divided by delta itself. Now, if all the critical stresses are same, sigma 1, 2 and same is equal to P, then the equation 13b will become 3 into P, 3 lambda plus 2 mu into gamma, or 3P by lambda is 3 mu plus 2 mu. Similarly, from equation 3, similarly from equation 14a, we have, if we put the value of K here, and if pressure P, K multiplied by delta, and P by delta is equal to 3 into mu, we put the value of P dot delta is equal to here, and say that 1/3, 3 into lambda, 3 into lambda plus K itself, P by delta. 1/3 P by delta. So that's the bulk modulus of elastic strain. For isotropic fluid, let us do Levy's constant through an equation 14b itself. This is the Levy's constant, this is bulk modulus, so they are related with this solution itself. Now, what is the Young's modulus of Poisson's stress? We know the Young's modulus is from the equation 13b. Sigma 1, sigma 2 and sigma 3 is given as 3 into lambda plus 2 into mu into delta itself. So delta is equal to 3 of sigma 1 plus sigma 2 plus sigma 3 divided by 3 into lambda by 2 into mu. Now if we substitute in equation 4a, substitute the value of lambda in the equation 4a, what will happen? Well, which has sigma 1 is lambda into delta plus 2 into mu plus epsilon 1 itself. Equation 13b, not 4. 13b. Where we assume 13b is here, sigma 1 dash, sigma x dash plus sigma y dash plus sigma z dash equal to 3 into sigma 1 plus sigma 2 plus sigma 3, 3 into lambda plus 2 into mu. Now, if we put this value here, put these values here and simplify, the value of sigma in equation 12c, what will happen? H. Then the Bagchi modulus. এটাই আবার ফিরে এলো। That's the Bagchi modulus for a cycle. এইটা কি হচ্ছে রে এখানে? Thus, epsilon 1, if we solve this equation, it will take this particular shape, lambda into mu plus mu, 3 into lambda plus 2 into mu, multiplied by delta 1 plus lambda 2 into q, it will be 1 lambda 2 plus lambda 3, etc. And it will become from elementary strength of material, epsilon 1. We know that epsilon 1 is equal to 1 by epsilon 1 minus gamma cap epsilon 2 into epsilon 3. By the Young's modulus, V is the Poisson's ratio, etc. Compare this with equation 15. What we'll find? 1 by P is equal to 3 lambda plus 1 by U here. And V is equal to A lambda into 2 plus lambda into mu. So E has become this equation and gamma has become this equation, lambda plus 2 into mu, etc. Now, what is the relation between elastic constant? We are familiar with the Young's modulus E, Poisson's ratio gamma, and shear modulus or modulus of rigidity G, and bulk modulus K. Among these, only two are independent, and E and gamma are taken as E and gamma is taken as the independent constant. Otherwise, G and gamma are expressed as with this relation itself. Okay, let us stop here. Thanks for your patient hearing and coming. Only 3 hours arrived today.